so the next special force to introduce you to is friction. Okay, so friction is actually another force that is actually really complicated if you want to have a really good understanding of it. But fortunately, we're going to take the simple route. Now, why is it complicated? Well, on the surface, you might think, well, if something is rough, there's more friction, so I just need a way to calculate that. But think about it. Let's say if I have a box, right? If I again have a box and it's on a very rough surface, like say it's very spiky and a very smooth, by that I mean very flat surface, and then I push it. Which surface, do you think the spiky one or the smooth one has more friction? Let me draw that out. Think about it while I'm drawing this out, right? So I have a box, right? It's on this surface and a box on this surface. Okay, so I'm going to push it the same way. Which one will experience more friction? Now, so naively, you might think this one has more friction. This one has less friction, right? The rough one has more. But if you think about it microscopically, if you zoom right in, if this is really jagged and bumpy, there's less contact points, right? It's contacting the box on the bottom. Let's say both of them is a glass box. So this is glass on glass and then glass on spikes. But there's less contact points, so there should be less friction, right? So I won't go through. I won't give you a complete answer, because if I need a complete answer, that's an engineering question, not a physics one. What do I mean is you have to zoom in into the microscopic view and understand the relationship between this and all the different types of texture, the different types of material. So that really goes into more engineering and material science. And we want to just understand the general laws of how physics work, because essentially that basically behaves like the basic laws as well. So we want to understand basics before we delve into all the different complications of things. We won't build sort of the microscopic version of microscopic theory of friction, but we'll look at the macroscopic idea. So another word to say that is the effective model. An effective model, the macroscopic model for friction. Okay, so in physics, in some sense, all physics is modeling. We're trying to find a simple relationship. What's a model? A model is a simple relationship, like F equals ma. It's in some sense a model. It's an equation, a simple equation that you can use to make predictions. Okay, that also sort of describes and summarizes all objects' behaviors. So, for example, F equals ma or W equals mg, the ones that you've learned, all objects behave to that. It sort of fits into that little equation. All right, so what we're going to do is, number one, we're going to zoom out and not worry about the microscopic view. And secondly, we're trying to develop sort of a simple relationship between that. So what I'm going to do in the next couple of minutes is to guide you through. I want you to think of, if you are the first person trying to understand friction, and you go like, I don't want to know the microscopic details. I just want to know overall, how do things react to us? Then how would you go about understanding friction? So this is really the key of physics, of learning how to understand the world, right? Okay, so first of all, you would do some experiments, right? You take some boxes and then you push it, and you see some will go farther than other on different surfaces. And you also realize friction appears in two forms. There's a friction where if something is moving, there's friction which slows it down, right? It will slow it down. But also, even when something is static, that it stays still at rest, it still has friction. How do I know that? Because I can put something on a slope. If it's rough enough, if it doesn't have friction, it'll slide right down. But if it's rough enough, it'll stay there, right? So how does it stay there? Well, let's analyze the free body diagram first. Well, there's the normal force as we understand. There is its weight, which will be pulling it down, or gravity will be pulling it down. But if you add these two arrows, right? So if I add this two arrows, well, if I want to do it quantitatively, I'll need to resolve the vectors. and do it component and add all the components together. But let's just do it geometrically just to get a sense, right? So if I move this over here, right? So if I take W, move it over here, and like this, so the effective, so the resultant net force would be here. So it will like N plus W will move it down here. But if the surface is rough enough, I can make it not move. That means I can have a friction, right? Just counteracting the N plus W, right? So this is the N plus W, and I can have a, so even if I can actually have a scenario where the surface is rough enough so that we have this free body diagram, okay, where the friction just about counteracts the sum of W plus N in a vector way, like this. Okay, so what we have concluded immediately is there's two types of friction, and you'll give them a name. It's called static friction and kinetic friction. Okay, like that. Okay, so let's give a definition just to be rigorous. So kinetic friction is slightly easier. It's the force on an object by the surface, and that does something, but this is the same, okay? It's the force on an object by the surface. And what it does is it resists motion, right? So it slows things down. And if the object is going this way, friction always works against it. It might be going faster. So the friction, if you're pushing it quite, so let's say you're pushing it, right? You're pushing it with quite a large force, then you can overcome the friction and have it move, but it still sort of slows down that motion. In the static case, it doesn't really slow it down because it's already static. What does it mean by slowing things slower than static? It doesn't make sense. So what we say is it resists the tendency of motion. Okay, so these are the definitions. I'll emphasize it, right? So the equal sign with two dots is saying that's the definition of this terminology. Okay, so just to emphasize the definition, so kinetic friction is the force on an object by the surface that resists motion. And static friction is the force on an object by the surface, again, same thing, that resists the tendency of motion, because there's a tendency without friction. So how do you determine the direction of the friction? We'll talk about how to calculate the magnitude later on, but the direction is easy. It resists motion, and if it's static, it resists the tendency of motion. And you think about it by thinking, without friction, how would this move? Without friction, it will go down that way. So friction must be holding it up that way. Okay, so that's how you determine the direction of it. And a property, again, common for both, is always parallel to the surface. So the direction is always parallel to the surface, but one resists motions and the other resists the tendency of motion. Okay, and good. All right. So what does it react to? At first, so let's think about the kinetic version first. See if we can come up with some sort of model, some sort of formula for it. Well, at first you would think that the heavier it is, right? What do you think the friction force would depend on? It might depend on the weight, right? That's probably one of your first guess. The heavier it is, it will probably have more friction. That's your intuition, and that kind of makes sense. However, let me try to challenge you this, right? If I tie this to a string with some helium balloons, so all right, so there's a tension that's sort of lifting it up. Okay, so there's a weight and there's a tension, all right, and let's say the weight is 10 newtons. And there's a tension where there's a helium balloon or just someone pulling it, whatever. I just want this to be flexible as this moves along to be sort of 9.9, right? So there is yeah, so this just about does not lift the whole thing off the ground. Do you think this will reduce the friction as it slides along, or does it have no effect if you sort of lift it off the ground with a little bit of force? And I think your intuition will be correct, that it will reduce the friction. All right. So how do I quantify that? What's actually reduced over here? It's not the weight. By tying it to the balloons, it's not the weight that got reduced. It's the normal force that got reduced, right? Let's analyze this properly, right? So technically, there's also a normal force over here, right? So what must be the normal force over here? Well, you can set up the correct equation like T plus N equals to W. And then the normal force is W minus T. W is 10, T is 9.9. So the normal force is 0.1 newtons like this. Or you can just, let's not use double N, we'll understand it's in newtons. Or you can just look at this and say, hey, that's 9.9, that must be 0.1 to counteract that. That's also okay. This is just formalizing what you intuitively know. So by tying the balloon over there, what you have reduced is the normal force. So it seems like if you are the creator of the theory, right, you want to create a model, you want to create a hypothesis. Essentially, that's how science works. You create a hypothesis and you test it over and over again and see if that hypothesis works over and over. If it works over and over again, congratulations, you have a law. you create a law or a model under your name. So the friction should be proportional. This is what I will propose. It's proportional to the normal force, not the weight, okay? Of course, if there's nothing pulling it up, so if T is 0, right, then the normal force is the weight. So the friction is proportional to the weight, but that's a very special case. More generally, right, if you had your first theory being proportional to the weight, I can falsify that by what I did, right? So making it is effectively lighter. It's not really lighter, the weight never changed. It's just that effectively is lighter. It means the contact with the surface, which is normal force, is lighter, okay? So the friction depends on, it's proportional to this. So the larger the normal force, right? So the larger the normal force, the larger the friction is, and the smaller the normal force, the smaller the friction is. So remember, when some things are proportional, we can write it with a constant, and the convention is using mu, like this, okay? Now, we also need to talk about static friction. So let me specify this is kinetic friction by putting a sub k, and it's also a convention, right? So to put mu sub k over here, it depends on the normal force, right? So this is equation number 1 that you want to learn. It's the equation for kinetic friction. So now let's also talk about static friction. So imagine I have this box on a ground like this, and I'm trying to push it, right? And so let's start off with this is being static. And of course, even though there is friction over here, right? If I push it hard enough, I can overcome it. But if you push it very gently, the friction would sort of push back, okay? So let's draw the free body diagram, right? So that's the push, right? And there is also the weight and the normal force like this, which should balance because it's not accelerating up or down. Okay. Now, if I apply a small amount of push, then if it doesn't move, we all have an experience, right? You put a fridge in front of you, you try to push it with just a little bit of force, you can't move the fridge. But if you push really, really hard, at some point with a lot of people helping you, you can push it, you can overcome it, right? So in some sense, you would realize that the static friction actually will be a function of how much you push, right? It will depend on how much you push, okay? And this is one of the other weird forces that actually reacts to and depends on external influences on it. Usually forces don't do that for you. But this one does, right? So let's say this is a fridge, you apply larger and larger force, pushing force. At some point, you will be able to push it. But if let's say you never were able to push it, then at first, the friction would be a little bit if you apply a little bit of force, but if you apply more, the friction would be more, resisting the tendency of motion. And if you apply a large force, then the friction will be very large. And at some point, there must be a maximum that friction. So that when you push it harder than that, then you'll be able to overcome the static friction, and it will become a kinetic friction situation, right? So number one, let me just make some space for myself. Number one, realize that the static friction depends on the external net forces. Okay, and number two, it has a maximum before it becomes a kinetic friction scenario, right? So at some point, no matter how much friction there is, I guess you don't necessarily have to always be able to overcome it, but generally, if you push hard enough, for any rough surface, if you push hard enough, you'll be able to overcome it. So it has a maximum. Okay, so what we should analyze is not Fs, because Fs depends on the pushing force, which is very complicated. But let's analyze Fs max. Okay, the maximum static friction you will get. What will it depend on? Well, it will depend on microscopic details or on the surface. But the heavier the thing is, even with the same surface, right? Let's say on the same carpet, you put a fridge and you put a textbook, right? You can easily push the textbook. You cannot easily push the fridge. So you might, again, think that it's proportional to the weight. But I can go through the same argument there is, hey, but imagine if there's a helicopter pulling a tension, lifting the fridge, you can probably, so that it's almost off the ground, you can easily push the fridge as well, because it's lifting up most of it. So what it really is reacting is not to weight, but again to the normal force. So when something is proportional, and we'll not repeat the argument, you can write down there's a constant, and we'll differentiate or distinguish this. That's a kinetic constant, and that's a static constant. So this is the formula for it, okay? And sometimes it's written as Fs is less than or equals to mu Sn, like this. Okay, and sometimes, just to show you all the different ways books will write this, right? Sometimes they will combine both together and say the friction, whether it's static or kinetic, is equals to mu static or kinetic, and like this. So a couple of comments over here. Whenever someone writes equal, even when they're talking about static, when they write equal, I'll put that back in a second, but if they write equal, what they mean is they're talking about the maximum. Where was it? Here. Yeah, they're talking about the maximum static friction, because it actually depends on the applied force over there. Okay, so when they write equal, just remember it refers to the maximum if they're talking about the static case. Okay. And comment number two is that, so this has a name, right? So this constant has a name, and this is called the coefficient of kinetic friction. And can you guess what that is called? It's the coefficient of static friction. And this basically, what it does is it depends on the microscopic details of the surface. So I'll put it over here just to keep everything on the same board. Mu S and mu K depends on the microscopic details of the surface. And I'm putting this in red to let you know that we don't need to know how we calculate this. That is a material science problem. Basically, well, what you can think of is a lot of material scientists did a lot of different experiments, and then they found a table, and that's what you do. So if you go to your textbook, you can look up the table, and let me find out what page it is. It's page 113. So you can go to page 113 in your textbook, and there's a table of a list of numbers. So basically what these material scientists did is they go to a lab, and then they take different types of surface, and then they apply some sort of, they put it in this free body diagram situation, and then try to measure this for different types of surface. So you can look up the surface of wood on wood, ice on ice, or different types of surface, and you'll have these numbers, which we will just take them for granted and use them to do our calculations.